In this lecture, we will discuss how to express power in terms of current and resistance, voltage and resistance, and also in terms of conductance. We will then perform some example problems, and then we will define resistance in a short circuit and an open circuit. We are looking at objectives 1, 2, and 3. 1, to understand the symbols for and the behavior of resistors. 2, to be able to state and use Ohm's law. And 3, to know how to calculate the power for a resistor. All right, let's take a look at how we draw current entering a resistor. Standard format is that current will enter the positive terminal of a passive element, and our equation for power would be P equals VI. In the text, they show a couple ways of current entering. The first is the current enters the positive terminal, and the second is the current enters the negative terminal. After chapter 2, you should not see this format, since that is not the standard, but rather you will see this format. So for example, this 8 ohm resistor, we would assume a voltage drop across, and the current enters the positive terminal and passes through the voltage drop and exits the negative terminal. All right, so we know that Ohm's law is let's restate it here. Ohm's law is V equals IR. Now, if we want to express Ohm's law in terms of current, to define current, we would say I is equal to V divided by R. Or in terms of voltage, V equals IR. Now we know that power is P equals VI. Now if I want to express power in terms of current and resistance, I would use this value for voltage, which is here, and I would plug it in. So P is equal to IR times I. So P is equal to I squared R. So we now have an expression for power in terms of current and resistance. Expresses power in terms of current and resistance. All right, now let's look at if we know the voltage but not the current. So we said our expression, Ohm's law, expression for current is this. So P equals VI, and let's substitute that expression into current here. So power is equal to voltage times voltage over resistance. So our expression for power becomes V squared over R. So now we are expressing power in terms of voltage and resistance. So we have two new equations for power, which gives us a total of 3 equations for power. All right. Now let's talk about power expressed in terms of conductance. Sometimes a resistor's value will be expressed as a conductance rather than as a resistance. So when we use the relationship between resistance and conductance, which we know conductance is equal to 1 over the resistance, or resistance is equal to 1 over the conductance. So we can substitute. So we now have power is equal to VI. That's one equation. We have power is equal to I squared R. And we have power is equal to V squared over R. Now let's express these two in terms of conductance. So R is equal to 1 over G, so it'd be I squared over conductance. And 1 over R is G, so this one would be V squared times conductance. So we now have P equals VI, P equals I squared R, P equals V squared over R. Power is equal to I squared over G, and power is equal to V squared times G. So we have 1, 2, 3, 4, 5 different ways to express power. So we have a variety of methods for calculating the power absorbed by a resistor, and the power delivered by active sources. So this would be power absorbed by a resistor. So if it's absorbed by a resistor, our power value should be positive. This is an expression of power delivered by a voltage source or a current source. Okay, so since it's delivered by, we would expect that value to be negative. All right, let's look at some examples. Okay, in each circuit, we will calculate the value of voltage and current. And then we will determine the power dissipated in each resistor. All right, so let's set some lines here. And I'll try to stay within the lines. All right. So, in our first circuit, we are given current and the resistance. So we know that the current is equal to 1 amp and resistance is equal to 8 ohms. And so we need to find voltage. Well, how do we find voltage? Voltage is equal to, let's give it a, voltage is equal to current times resistance, which is 1 amp times 8 ohms. So our voltage here is 8 volts. All right, now the power dissipated in each resistor. So power in this resistor, let's express it in terms of I squared R, because we're given the current and we're given the resistance. So power is equal to 1 squared times 8, which is 8 watts. All right, let's look at the next problem. We are given voltage. Voltage is equal to 50 volts. And we are given conductance. So G is equal to 0.2 Siemens, which is equal to 1 over R. So R is equal to 5 ohms. So we can use either the value for conductance or the value for R, but we know Ohm's law. Ohm's law states that B is equal to IR, and if we express that in terms of conductance, voltage is equal to I over G. So in this example, current is equal to voltage over R, or voltage times conductance, which is equal to 50 volts. And I guess I should change my color to purple here, so be consistent. 50 volts times 0.2, which should give us 10 amps. Okay, now finding the power. So our voltage is given as such here, and our current is entering the positive terminal. But we can express voltage in terms, or power in terms of voltage, which is V squared over R, or V squared times conductance, since we're given conductance. So power is equal to 50 squared times 1/5, which is 0.2, which would give us 2500 over 5, which is 500 watts. All right, let's look at the next one. We'll switch our colors here. All right, so we have a current source, and we're given the polarity of the voltage, and the current is entering the negative terminal. So I'm going to turn that around, and I can say current is equal to, if I change it this way, then I meet my passive sign convention, which I like to do it that way. So if I do it that way, then I have to change the sign. So current is equal to minus 1 amp. And resistance, we're given resistance this time, and it is 20 ohms. All right, so using Ohm's law, V is equal to IR. So V is equal to minus 1 times 20, which would be minus 20 volts. All right, now let's find the power that's absorbed by that resistor. So we can use P equals, we're given current, so I squared R. So P is equal to -1 squared times 20, which is equal to 20 watts. All right. Our final problem here, we are given voltage. So this is our polarity here. And you'll notice that our defined current direction will be negative because it's entering the negative terminal. So voltage is equal to 50 volts. Resistance is equal to 25 ohms. So let's find current. Current is equal to V over R, which is equal, and the current that I am defining is going in this direction. So it's the opposite of that one. So we'll have to change the sign. So this is 50 divided by 25, which is 2 amps. And I sub D is equal to minus I. So it's minus 2 amps. Okay. Now, calculating the power. Because they give us voltage and resistance, we're going to define power in terms of voltage, which is V squared over R. So power is equal to 50 squared over 25, which is 2500 divided by 25. Power is equal to 100 watts. And that's a positive for all the resistors, because resistors absorb power, and that's what our resistors are doing. They absorb power. All right, let's talk about resistance in an open circuit and resistance in a short circuit, and what does that mean? Let's go with this color. Let's say that we have a circuit with a power source and a load resistor here. And this is a voltage source. And that's our load. If we remove the load, we now have what's called an open circuit. So what is our resistance value with an open circuit? Current travels through a voltage source from minus to plus. Hey, I like that. And it travels around and it gets to this point, and what happens? It cannot move, it cannot jump across this open area. So that tells us that our resistance here is infinity. So for open circuits, resistance is infinity. All right, let's take a look at a short circuit. We have, this time let's use a, I don't know, I kind of like voltage sources. We can use either. And again, we have our resistor load here. And we decide to remove this load and instead we shunt it. So let's use purple. What's shunting? It's putting a wire across. So go back to my color here. What is the resistance here? Well, we say that the resistance in wires is 0. So our current is traveling through our voltage source, and it keeps going around unhindered. So in this case, our resistance would be 0 ohms. So current takes the path of least resistance. So if the current cannot go through, then there must be a very high amount of resistance. If the current goes through easily, then there is little to no resistance. Okay, so we discussed the different forms of power. And to review, power can be expressed in terms of voltage and current. It can be expressed in terms of current and resistance. It can be expressed in terms of current and conductance. It can be expressed in terms of voltage and resistance, or it can be expressed in terms of voltage and conductance. So that gives us several ways to define in terms of a resistor or a conductor. That should be a C, conductor. Or in terms of a voltage source or current source, and or you would have both voltage and current. Okay. That concludes this video.